Basics of Statistics. Part 7.
Of the four statistical approaches, we have already covered comparisons and risk estimations. In this lecture, we will shift our focus to correlations. Correlation is a statistical measure, ranging from -1 to +1, that indicates the strength and direction of a relationship between variables. Let's begin by examining the correlation between two continuous variables. In this example, we aim to determine the correlation between dietary trans fat consumption and plasma cholesterol levels. So, in a cross-sectional study, we ask 400 healthy adults to log their food intake over 1 week, and at the end of the week, we measure their plasma cholesterol levels. This gives us two paired sets of continuous data for each participant. One way to visualize these two values is to represent them as one dots on the x and y axis. And by adding all the data, we will create a scatter plot. Here, by visual inspection, we can observe that the data exhibit a linear pattern. We refer to this unique line as the trend line or regression line. Observing linearity indicates the appropriate test to calculate the strength and direction of the correlation is Pearson's R. Our or correlation coefficient provides a value between -1 and +1. A value of 0 indicates no correlation. In this example, R equals 0.78. Since it's a positive value, it indicates a positive correlation, which means that as the x value increases, the y value also increases. Additionally, 0.78 is close to 1, indicating a strong positive correlation. If R were -0.78, we would observe a strong negative correlation, where the scatter plot would show that as the x value increases, the y value decreases. As the points become more scattered, the correlation weakens, and the coefficient value moves closer to 0. Returning to our example, even though we demonstrated a strong positive correlation between trans fat consumption and cholesterol levels, we cannot conclude that higher cholesterol is caused by increased trans fat intake. This highlights that correlation does not necessarily prove causality. Sometimes the trend line isn't straight, indicating a nonlinear correlation. If the line consistently moves in one direction, either upward or downward, we refer to it as nonlinear monotonic. In such cases, we can calculate the correlation coefficient using Spearman's R, which is interpreted similarly to Pearson's R. However, if the line changes direction, neither of these tests is applicable. One important point about correlations: if we have a linear relationship between two continuous variables but one or both are not normally distributed, it's preferable to use Spearman's R to calculate the correlation coefficient for assessing the strength and direction of their relationship. Another point about Pearson's and Spearman's R is that they are often presented with a p-value, and it's important to note that if the p-value is not significant, we cannot rely on the R value. Therefore, we should only report the correlation coefficient if the p-value is significant, and a non-significant p-value means there is no correlation. To quickly recap, correlation is a statistical measure that assesses the strength and direction of the relationship between two variables. When the variables are continuous, normally distributed, and exhibit a linear correlation on a scatter plot, Pearson's R is used. If the variables are not normally distributed or show a nonlinear but monotonic relationship, we use Spearman's R instead. The correlation coefficient ranges from -1 to +1, with 0 indicating no correlation. For both tests, a significant p-value is needed to confirm the validity of the R value. And always remember, correlation does not imply causality.
Thank you for watching.